Okay, today's lecture is lecture 18 of our semester. So now let's just dive into our next topic. So we are currently working with drift diffusion solver. So I think that our students already made the device simulator which can calculate the IV characteristics by using the Shapeter-Guman scheme. So now you can calculate, at least in the 1D case, for example in the case of a PN junction, you can calculate I as a function of V, but this is under assumption of a steady state. Steady state means that some quantities whose time dependency is just 0. So I think that although this simulation or steady state simulation is the very basic one and fundamentally important one, but in many cases we wanted to perform this transient device simulation. As I told you before, if we are working with, for example, logic device, then actually we don't need this kind of actually we need, but transient simulation is not of our first priority. However, if we are talking about, then it is really important to have the simulation capability to track the transient behavior. For example, you wanted to write number 0 to your device memory, and you wanted to write number 1 to your memory. So it cannot be done instantaneously, but it can be done only, for example, you apply, for example, first word line equal to 1 and bin line equal to 1. This kind of pulse should be applied to your device, memory device. After that, some time has passed, then your memory device remember the value applied, for example, in the case of bit line. So transient simulation is really important for some cases. So we need to consider this transient simulation. But you know, maybe you can ask me this question. We have already done several transient simulation. For example, in the case of our diffusion simulation, we already did it. And also in the case of our previous RC simulation, yes, we did the transient simulation. Then what is the difference between our previous transient simulation and today's discussion? So in my opinion, the main difference comes from the displacement. So displacement current. So let me just explain. So this material is just a typical one. So what is the difference between our previous steady state solution or steady state simulation and transient simulation? Yes, in the case of personification, we don't have any change, but in the case of a continuity equation, now we have time dependent term. Yes, we know it. And how can we treat it? Yes, we have already seen it before. So now this time dependency can be expressed as this form. So now you understand this is obtained with the backward Euler scheme. So if we adopt a more advanced scheme, then instead of this simply one single past value of our electron density, maybe we need more elaborated expression for this time dependency. But anyway, it is true that we can do it in this way. Once we know the history of this system, so now let's say that this is the time we wanted to calculate. And if we know all kinds of past history, then by using that history and present value, we can make certain approximation about time dependence term. So by using that one into this continuity equation, we can get the solution. So using this time matching scheme, and since this is quite easy to make this kind of discretization, so we have to understand this n past, this is just a given number, so we do not have any contribution from this term. But here we have solution variable electron density, so it can contribute, or it must contribute to our Jacobian matrix. So when we consider Jacobian matrix, yes, n past does not contribute to our Jacobian matrix, and yes, this term makes a certain contribution. Fortunately, in this case, the modification to the Jacobian matrix is really straightforward, because in this case we have just only one single number here, and it is not a non-linear function of our electron density. Once time step is given, then this is just a fixed number, so we don't have to change the Jacobian matrix. So also it is corresponding to a diagonal component, so it is easy to modify our Jacobian matrix. Okay, so it is not that difficult to implement our transient simulation, but real difficulty or real complication comes in this time. So please have a look at this slide more closely. Yes, displacement current is the real matter of implementation. So when we consider this terminal current, actually we did certain integration of electron current density and hole current density at a certain terminal area that was allowed in. So simply speaking, terminal current is obtained by this way: integral of total current density over terminal area. That is the general expression for our terminal current. For example, if we consider drain, then we must integrate our total current density vector over the drain content. Then natural question is, then what is this J total? So total here means that containing every contribution from every mechanism. In this case, we can identify the contribution from electrons and holes. Yes, that was what we did in our previous implementation, but now we have to have also another quantity obtained from this form. So time derivative of our displacement vector. So this term is called as displacement current density, and it should be included in our consideration. So, you know, if we introduce this term, then we can show that yes, the divergence of our total current density vector thus vanishing. So this is obtained from some equations we are considering right now, and it is consistent with Maxwell equation. Okay, now you know this one. So simply speaking, although you have already made many good implementations for your DC calculation, and when you consider your single device, then the only modification to your Newton-Raphson method is changing your residue and changing your Jacobian matrix, then you will get the solution. But when you get certain information out of your converged solution, so the most important quantity is this terminal current, and when you calculate the terminal current, you have to also modify your expression for terminal current. Please include this term. Then how can we include this displacement current contribution to our IV characteristics? So now let's think about a simple 1D system. Now in this 1D system, for example, let's say this is a node, and here we have the contact boundary. This is a terminal node, and what we do is usually, yes, we can evaluate here Jn and Jp. Maybe you make a sum of these two makes another current. However, also at this point, this midpoint, you can calculate this quantity. This quantity means the one corresponding to our displacement vector, and its time dependence or time derivative is required. So although I have written in this way, but what you have to do is actually this way. 1 over delta t, and evaluate your displacement at the present time point. Yes, you can do it at present time point minus, here you have also another one. This is corresponding to your past time point. Yes, so this first term is corresponding to the displacement right now, and this term is the displacement evaluated at a time instance delta t past. So now taking the difference and divided it by delta t, you can estimate this time derivative operation. Okay, so now by including this term, then now you can calculate the full contribution to your terminal current. Of course, when your signal is slowly varying, actually this contribution from displacement current is quite small, so you cannot see clearly the effect of this term. However, if you increase the speed of or the frequency of your signal, then you can easily see that this term becomes a dominant contribution to your terminal current. Okay, so you can later see that impact. So in my opinion, actually this is the most, although I have discussed about the transient device simulation, actually transient device simulation itself is not that difficult. So you can just consider a new term here, the time derivative terms, just adding it with the simple consideration with backward Euler or even higher order approximation. So implementation itself is not that difficult, but more involved thing is calculation of displacement current contribution, and please be careful when you implement it about its sign. So it is quite easy to make sign mistakes in this case, so you should be consistent with your other equations, so please be careful. Well, so simply speaking, transient simulation itself is not that difficult as much as you have already made well implemented this simulation. So now let's try to use it for our more realistic cases. So for example, in this lecture, I want to talk about mixed mode simulation. Here we have a certain new term called as mixed mode simulation. What is mixed mode in this context? So in the TCAD simulation, when we say mixed mode simulation, then it means that we are now solving a system contains device, multiple or single devices, and also lumped elements. So solving a coupled system of these circuit elements, that is called as mixed mode simulation. It has a historical reason why we call it as mixed mode. So when the very first device simulation was developed, of course we only consider a single device. So for example, if we consider p-n junction, then we just consider only p-n junction, p-type, n-type, and of course it has two terminals, and its terminal voltages are just given 1 volt, 2 volt, grounded. That was just given. So it was treated as just a single boundary condition. However, in reality, the actual circuit contains multiple devices, and in order to make a certain biasing on this device, we need a certain lumped elements like resistor or capacitor or inductor. All of these lumped elements are required to make a simple circuit. So so at the time it was clear that this is single device simulation and simulation of multiple devices or multiple circuit elements were clearly distinguished, because single device simulation of a single device requires a certain code, okay, set the boundary and what is the boundary condition and what is the doping, then we can solve that system. However, the simulation of multiple devices should require what is the net list, what is the connectivity between one single device and the other device. Are they connect? Are their first terminal and second terminals are connected or not? So this kind of information is required for the simulation of multiple devices. So therefore our previous researchers say that okay, in contrast to this single device simulation, so in order to make a simulation of multiple devices, we need certain additional capability. So they call it as mixed mode because why we say the mix? What is the mixture? In this case, they say that okay, this is device simulation is a typical area of TCAD device simulation. However, inclusion of lumped element, this is not a boundary of a conventional TCAD simulation. This is more related with the boundary of or area of circuit simulation. But we wanted to mix them all and make a better simulation capability. That was the original reason why we call it as mixed mode simulation. Nowadays, this kind of capability is just regarded as granted, quite natural, and of course our device simulation should consider that kind of mixture of devices and circuit elements. So nowadays this is just quite a natural one, but please remember historical development. We started from just a simulation of one single device with 1D structure. After that, we have gained sufficient amount of confidence on our simulation capability and expanded it to further and further. And where we are now currently simulating some small building blocks of our circuit with completely with our TCAD device simulation, and later we want to expand it to a larger and larger system. Okay, so now let's go to this simple rectifier case. Maybe you have seen it in your microelectronics course in your undergraduate age, and this is the very first one beyond a single device. In that course, usually we study the behavior of this diode. Diode shows a certain rectifying IV characteristics, I of V, and it says that if you apply negative voltage to this diode, then actually current is really negligible, quite close to zero. And after that, if we apply positive bias, usually called as a forward bias, then actually it can conduct current quite exponentially. So once after studying this behavior, external behavior, after that we include one single resistance to here, then apply the voltage entire across this system. Okay, so therefore, usually what we do in microelectronics course is, okay, treat this one with quite a simple expression. For example, this diode current can be expressed as quite simple one. For example, here we have a certain number corresponding to the ideality, and we can make this quite a simple expression for IV characteristics, and by combining these IV characteristics and Ohm's law together with this circuit connectivity, we can get quite a simple expression, and the program which can do this job automatically is typically called as spice. So when you have a spice program, then you can provide simple rule for describing each circuit element inside this circuit. Then it can calculate their behaviors. So usually people think that this is the field of spice. However, what we wanted to do today is, okay, here we have three different circuit elements, and here we have voltage source and resistor. They are treated as just lumped element, so they don't have any kind of internal quantities, and they are just specified their terminal characteristics. What is the voltage difference across voltage source? So that is just given as its electromotive force. And how about the current flowing through this resistor? It is given as just Ohm's law. It doesn't have internal physics, although it has internal physics, but in this description we don't care about it. So let's just think about this one. A person walks. In order to walk, so actually in the muscles inside in this person's body should move, and brain should send a certain signal to these muscles. However, when we describe a person walks in that simple way, we don't care about internal mechanisms to enable this walking. In this case, this guy just moves from one position to the another position. Quite similarly, in order to realize this battery, actually we need a certain chemical reaction inside this system. And yes, it was enabled by certain engineering effort. However, we don't care about this description, although that there really exists a certain chemical reaction, but it was just neglected in this description. And what we say is, okay, just their difference is given as electromotive force. So now you understand, for these two circuit elements, our description is really primitive and simplified. However, in the case of this diode, we wanted to do a much better job than describing it with this way. Describing the diode with this I equal to something like that, it just gives us the IV characteristics. So if we ask ourselves, what is the internal electron distribution and what is the internal hole distribution, or what is internal potential distribution? Well, by spending some effort, maybe we can recover the quantities. However, there is no guarantee that these quantities are properly modeled, consistent with TKD simulation. So instead of using this simplified expression in this mixed mode simulation, we introduce a certain coordinate system, and starting from 0 to L, and introduce many points, and for each point we solve a Poisson equation, continuity equations, and couple them all, so getting the same quantity. Now it is clear that this approach is computationally much heavier than our previous one. Well, if we do it properly, then maybe we will get the same result. What will be the output voltage when we apply certain input voltage? So if we do it properly in SPICE scene and this TCAD scene, then if they are consistent, our output voltage will be the same. Yes, that is our eventual goal. We wanted to make a certain consistent modeling set, even in terms of spice modeling. But unfortunately, now let's think about this one. Now you are just developing a certain diode technology. So you don't have a well established model for it. And its parameters are always changing. So in this case, your spice simulation cannot clearly reproduce the accurate result of real actual fabricated devices. That's the problem. So once everything is well established, then spice model will play really good role and critical role for enabling design of a massive circuit. However, at the early stage of its technology development, we need a certain effort in terms of ticket. So please think about the main research area or R&D area where TCAD is frequently using. So in that case, actually we have no well established technology, because TCAD is usually applied to the development of a next generation device. Well, we don't have the technology taped out, or yes, that is a problem. Or sometimes if we have some problems in well established device, but if we don't have any clue about the main root cause of that problem, so maybe TCAD can play a significant role. Okay, so I think that I have already covered the contents in this slide. So yes, what I wanted to do is in this slide, if we wanted to, if we already know the IV characteristics of this single device, then using this single device characteristics by performing additional graphical analysis, now we can calculate this certain output voltage. So this is a two-step method. One step, the first step is identifying the IV characteristics of each component. After that, collecting them all by solving it in a spice level. So spice can do it. Then who can provide us this kind of this blue curve? Well, if you change your, for example, dose of your ion implantation, or if you change the temperature of your dopant diffusion, so then what will happen to your PN junction IV characteristics? So this kind of information cannot be obtained solely from this spice model. Well, anyway, once we get this IV characteristics, after that calculating this circuit level analysis is not that difficult. But in our so-called mixed mode simulation, instead of taking this two-step approach, we just want to one-shot approach. So how can you solve this one? Include this resistive component into the part of our entire system and solve them all, yes, in the same way we did with this TCAD simulation. So actually, general implementation would be quite involved. For example, this is one simple LC oscillator. So you can identify L, inductors, and capacitors. Where can you find the capacitors? Yes, they are capacitors. They are actually not a lumped capacitor, but they are MOS vector So varactor means that variable capacitors. This is nothing but just MOSFET whose source and drains are connected together. So they are just working as a capacitor. So when we have proper values of its substrate, then we can use it as a variable capacitor. Okay, so anyway, you can find that it has two inductors and two capacitors, and by using these two LC pairs, we can construct on a simple oscillator. And we need to analyze this kind of simple circuit. Then how can you treat the TCAD level analysis of this system? Well, in that case, of course, what we have to do is this inductor can be treated as a lumped element. Okay, it's okay. It can be treated as also this guy can be considered. Then how about this varactor? Then first of all, we have to make certain, how can I say, certain two-dimensional or three-dimensional structure for MOSFET. After that, connect their source and drain in one contact. Then we can realize this varactor. And you can see that here we have N MOSFET. Yes, we need the structure file for these N MOSFETs. And here we have a P MOSFET. Yes, also we need certain device structure file for P MOSFETs. And how? Okay, now let's assume that we have several devices and several structure files. Then how can we analyze the entire system? For example, you can ask me this question. Okay, here we have a P MOSFET. Then first consider this P MOSFET and extract its IV characteristics. Also here we have N MOSFET. Yes, so also by performing the DC simulation, we can calculate IV characteristics and make its IV model. But point is, this is not a steady state circuit. This is oscillator. Oscillator means that your signal is swing between the its minimum value and maximum value, not in small signal way, but in a large signal way. So simply speaking, it is almost impossible to consider just this one, this IV characteristics. Okay, if your oscillator oscillate quite slowly, then the DC description is completely okay. However, usually what we want to do is to use this kind of RC oscillator for your RF circuit, radio frequency circuit, operating several gigahertz or several 10 gigahertz. So in this case, transient effect cannot be neglected at all. Well, okay, then maybe we can do it better. Instead of just considering only DC component, of course we can include a capacitive component by performing certain kind of small signal analysis. So, for example, in this analysis, even though we have DC already, then we can also include a certain capacitive component between gate and source and gate and drain or something like that. All kinds of capacitive components can be added and make a much better model for our MOSFET. Point is, this kind of capacitive component or sometimes resistive component, they are really dependent on what? They are really dependent on the voltage condition. We need also certain table for these parameters. Yes, we can do it. So, so, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, this is actually what we do in reality. When you have a certain MOS device, then the guys who are working on the PDK process development kit should extract the DC characteristics and also its AC characteristics and make a good compact model for this device. Then only when we have a good model for this device, good compact model, then circuit designers can perform quite good circuit simulation and design something. But point is, well, extracting DC and extracting this AC parameter, that takes a certain time. How can you extract these parameters? You must do certain kind of measurement. Fabricate it, measure and make a good model, and once again verify your model. Then, well, I did it, and if we send it, then maybe there can be certain discrepancy, then there can be feedback from our designers or customers and improve our PDK model repeatedly to deliver successfully developed PDK. This is the job of PDK engineers. Okay. However, although this is the general procedure, but at the early stage of technology development, actually this measurement is not possible. So if we are talking about, for example, CFET, then do you have the working CFET at your hand? Actually, not. No. Actually, after of 1 month later, you will see more result for state of the art CFET devices. So we are quite much expecting those results. However, point is, well, if we have to make an early stage of design with undeveloped or underdeveloped technology, actually this kind of measurement is not allowed. Then how can you make this PDK? That makes certain problems. So what we do in this case is, okay, instead of considering all kinds of this information transfer from the real fabricated device into well-established PDK, we can just do the TCAD simulation. Question is, well, then is your TCAD simulation is fully compatible with the actually fabricated devices? This is another question. So, although you have a certain TCAD simulation, but there is no guarantee that your TCAD simulation always perfectly reproduce the real fabrication device. Then the, how can I say, the correctness of your TCAD simulation should be guaranteed by your TCAD engineers. Your TCAD engineers should their input parameters or device structure or material parameters, mobility models, those kind of things should be calibrated to make a good agreement. However, this is also everyday life of TCAD engineers. So we assume that currently we have a well-established TCAD model, although it is not easily transferred to our PDK model, but now we have a TCAD model. And with this TCAD model, now we can perform this complicated system. So solution of a complicated system. So do you have any question on this motivation? So if we understand this motivation, the later thing is quite easy. So in general, we need a certain capability to process netlist file. So when you place a certain arbitrary number of elements in your circuit system, first of all you should be able to describe them, and there is a standard method to describe this circuit, that is netlist file format. So yes, once with this netlist file format or your independent file format, then you can process a certain device system. After that, by connecting them all, couple them all, you can calculate this problem. Okay. Well, considering the general situation would be quite involved. However, in our lecture material, we have introduced really simple case, quite a simple case without processing or passing that list file. Let's say that a resistor is attached to a terminal. Then how about this one? Let's say here we have certain circuit or terminal area. For example, this can be, for example, a drain or source or a gate. At this plane, what you did in your previous lecture was, okay, we can define total current density vector and integrate this vector over our terminal area, and by taking its negative value we can get the terminal current. That this plane is the drain contact surface. However, now let's say that here we have certain point whose voltage is VI external. So here I is used to identify your terminal. For example, in this case we can say that drain terminal, but not internal but external. Then what is this? At this point we introduce drain terminal but not external but internal, and now we assume that between them we have a certain resistance between them. Well, maybe you can ask me, this kind of thing is quite unnatural, but let's think about this case. Sometimes we do this kind of modeling approach. For example, what is it? This is a gate contact, and this is our silicon substrate in the case of planar MOSFET, and of course here we have a source and drain region. Usually what we do with our modeling approach is, okay, we consider just a part of our entire device system, and by performing, for example, spice modeling or ticket modeling, we get certain information. However, actually when a user, an engineer, try to apply certain voltage, it cannot, or he or she cannot directly insert a certain voltage on this plane and on that plane. It is not possible. What they can do is, there is a certain metal plate and there is a certain metal plate far away from this one, and what we can do is just to connect a certain metal tip and another metal tip and apply certain voltage to this metal tip. In this metal pad, of course, there is a metallic connection between this metal pad and our source region, and also there is another metallic connection between our metal pad and internal drain region. And since they are all out of good metals, so actually we have a relatively small resistance. Also we have a small resistance. Good. And also here we have a silicon part, and they are highly doped, and this part is highly doped. So ideally the resistance between this metal pad plane and this internal boundary of our TCAD simulation or SPICE modeling, the resistance between these 2 points should be minimized. However, in reality, it is no longer negligible. Actually, it provides us considerable amount of resistance. So, therefore, what we do is just like this. Here we have a good model for internal device. This one is actually corresponding to the lead boxed one in my drawing, and additionally we add more component to the source and drain, and they are called as a parasitic source drain resistance, or sometimes access resistance, or whatever. So following that way, we can introduce this kind of another lumped element. So this one sometimes can consider all kinds of parasitic components, or sometimes it can include or it can represent this intentionally added lumped element. So they can be expressed in that way. So what we can do is, once we know this internal drain voltage, then we can actually solve the system. However, what we know is not internal density, internal voltage. What we know is only external voltage. So we need certain relation between our known, this is known external voltage, and unknown internal voltage. Okay, by performing voltage drop between this internal and external and internal using the terminal current, we can easily obtain this internal voltage. So are you with me? So simply speaking, in this simple case where only a resistive component is attached to our internal terminal, then previously we had to solve this way. Our drain internal was given as our drain external. So for example, when you apply 1 volt, then actually you just solve your applied voltage is 1 volt. But now it is no longer the case. Although you apply 1 volt, let's say you have 1 micro amp as your, how can I say, your drain current, and internally if you have resistance like 1 kilo ohm, then voltage drop across this resistive component becomes 1 millivolt. So although you apply 1 volt, but actual value you apply to your internal drain contact is no longer 1 volt but 0.999 volt. So that should be considered in this way. So simply speaking, yes, please use this internal one instead of this external one. Yes, it is not that difficult. Well, then what is the modification? Point is, now you need current as another unknown variable. So this makes a really big difference. Please think about your previous implementation. Did you include your terminal voltage or terminal current as unknown variables or not? Actually, you never consider them as solution variables. You consider just electrostatic potential and carrier densities as unknown variables, and by solving your Newton-Raphson method, then you get their profile, and at the end of your solution procedure, you just reconstruct your terminal current out of potential and electron density, hole density. But now, when you consider your mixed mode simulation, actually you need include terminal voltage and terminal current into your solution variables. Well, then means that now your solution vector just looks like this. There is a long list of your electrostatic potential, electron density, and hole density, and at the end of your solution vector, grand solution vector, now you need your I and V variables at the end of it. Well, then how does it look like? Now your Jacobian matrix now should be changed in that way. Now let's say if this is the case, now your phi and P and IV, then your Jacobian matrix is also little bit expanded. So this large part is just the same as before. However, now you have a quite a small part for your IV variables, and you need also another one here and there. These parts are quite important. What is it? So this part just says that instead of a given number, now you have to solve your internal equation with your terminal current and voltage. Actually, in this case, major contribution is obtained from your internal voltage. And how about this part? Here we have the part. So these lowest laws are devoted to the description about your voltage and current. So in order to fill these laws, you need certain information about terminal current in terms of internal quantities phi and P. So already you did it. What you did is, once after the simulation is over, out of your phi and P, you calculated the terminal current. However, that was just processed as post-processing. It was not included in your Newton-Raphson method. But now you have to explicitly write down the expression for your drain or terminal current and calculate the Jacobian matrix for that contribution. So that is a little more complication obtained with this kind of a constellation. Okay. However, although it is a little bit tricky, but it provides you quite more capabilities. Now, not restricted to just a single device, but you can now expand your analysis to the multiple devices. Okay. So here we have an example. So please try to solve this one. So point is, although actually calculating this curve is not that difficult, you can do it in a various way, but point is you should be able to perform you should be able to perform this example with mixed mode simulation capability. Point is, in order to develop the mixed mode capability, you have to include the I, V variables into your unknown variables. That is the key. Okay, so please do it. And let's just combine these two new simulation capability. Mixed mode, transient. Yes, now you can do it. For example, this one shows the same rectifier, but I just lamp our input voltage from 0 to 2 volt quite slowly. Slowly means that within 2 seconds I just increase it from 0 to 2 volt. It means that I just increase 1 volt within 1 second. So this is forever. However, if we increase our input signal from 0 to 2 volt within 2 picosecond. Wow, picosecond is corresponding to 10 to the minus 12 second. So which is much faster. Oh, well, 10 to the 12 times faster than previous case. Then now you can see that this is the response of your rectifier system. What you expect is, okay, so there is a certain voltage offset. After that, yes, quite similarly, there is a certain voltage offset. After that, just input is copied to the output. However, if our operation speed becomes too fast, then actually it cannot follow that expected behavior. So simply means that please do not try to operate this rectifier with such a high fastly varying signals. It is not suitable for practical application. If you wanted to use it, then please reduce the speed of your operation. Another example is sinusoidal, the same system and sinusoidal signal. Once again, blue is input and red is output. What you can see is, okay, when you apply sinusoidal signal, then it can provide us this kind of behavior. Wow, now you can see that although we have applied just a simple sinusoidal one which has only one single frequency component, but now due to the non-linearity, now our signal, output signal, red one, has this kind of behavior. So it can contribute multiple frequency components, not only this fundamental frequency, but it can generally consider its integer multiples. Fundamental, 2 times fundamental, 3 times fundamental, many kind of harmonics of this fundamental frequency can be generated by this rectifier. This is the one we have expected in our example. For example, this is given in 100 megahertz. Okay, so 100 megahertz is the period is 10 nanosecond. So in this 10 nanosecond period signal, it works quite properly. However, now let's try to make it 100 gigahertz, 10,000 times, 1,000 times higher than before. And now you can see that this is the very first period or very first response of our rectifier. Can you what is it? Actually, this red curve cannot be expected from its steady state behavior. Of course, this is just transient behavior, and we have to wait for a while to get its how can I say, stabilized behavior. But anyway, we can clearly see that the behavior of our output voltage is much different from our previous steady state one. So practically this kind of behavior or this kind of information is really important. For example, once again, such a high frequency operation is not usually done in our memory devices. Memory device, the operation of a memory device is governed by other aspect. However, when you consider logic device, actually the maximum frequency we can use this logic device actually determined by its frequency behavior. So, for example, if we have a certain logic technology whose capacitive components are quite huge, then we cannot make rapidly reacting inverters. Then it means that we cannot use it for high frequency operation or high clock speed. Okay, so now let's wrap up today's lecture. So simply speaking, what you have to do is please try to implement transient DD solver, which can consider the terminal resistances. So at your two terminals, you can specify the arbitrary value of terminal resistance. For example, for your cathode, you can specify certain quantity, and for your anode contact, another terminal, you can specify another terminal resistance. So by using those ones, please just try to reproduce the result of our examples. Okay, it means that you need two different efforts, implementational efforts. One is make the transient one, and another one is mixed mode one. So I'm afraid that actually each of them is not that easy. So in my opinion, transient implementation of a transient is actually not that difficult. Maybe you can easily get the converged solution, but when you try to estimate the displacement current, then maybe such complicated sign conversion can make some problems. And after that, also inclusion of resistances into your system or expanding the unknown variable vector a little bit, that can introduce some problems, because I'm certain that both of you already use certain conventions like multiple of 3 is corresponding, or remainder of division by 3 introduces some classification of your unknown variables. For example, potential electron hole. So if you have a number 3, then this is corresponding to the electrostatic potential at your node index 1. However, if you extend it to this way, if you include more variables, and actually this kind of a simple rule obtained from division by 3 cannot be applied beyond a certain maximum number. So please be careful about your indices. So actually, the treatment of indices is really critical for realistic development. For example, right now we say that we have just electrostatic potential and electron density, hole density as a solution variables, but in reality user can specify which equation should be solved or not. So in reality, in practice, your solution vector can be just a mixture of many different components or many different unknown variables. So in that case, how can you label them and track them consistently without any problem? That makes quite practical difficulties to your real implementation. But our course is just devoted to the beginners of this development. So let's just assume that. So for first some numbers, they are devoted to the electrons and holes and electrostatic potential. And at the end of your solution vector, you just add terminal currents and terminal voltages. Although I just shown you only a node, please consider both of your left terminal and right terminal. So if you have 3 terminals, actually you should add 6 more unknown variables. Your first, second, third terminal should have also their own terminal currents and terminal voltages simultaneously. So please be careful about tracing their indices. Okay, then although this can be a little bit tricky, but I will just allow 2 days to perform this homework. So please try to do your best. And yes, although one remark is both of you guys told me that you will develop device simulators. Although one is for IGGO device and one is for silicon device. So as much as you are working with that kind of device simulation, then actually this kind of capability is critical for your term project also. So please do not restrict yourselves to this homework due. Even though you cannot finish it, but please keep developing this capability. Okay, then let's wrap up today's lecture and see you this Thursday.